Good day, engineering students. Today we're looking at chapter 4 in your engineering science that talks about statics. We're just looking at a simply supported beam with point loads and a uniformly distributed load. I am your facilitator, Mrs. Ndaba. These are all the keywords to remember as we go through the course. These are the different particular cases that a beam can be loaded. We're looking at this beam. We've got the weight of the beam. We've got a UDL of 80 kilonewton per meter. We've got R1, R2. We've got the 50 kilonewton concentrated load. What do we need to do here? We'll be calculating the magnitude of R1 and R2, calculating the bending moments, and drawing the shear force and the bending moment diagrams. Our first step is to calculate the magnitude of R1 and R2. Now, when we calculate R1 and R2, for the first one, we're going to look at the moments, the anti-clockwise moments about R1. Now, if we look at the anti-clockwise moments about R1, we have the first one, which is our total, which comes from 80 multiplied by 5. So that will be the first one. 80 multiplied by 5 will be 0.5 meters away from R1. So it will be 0.5 meters away from R1. Then next, we've got our 50. Our 50 multiplied by 12, which is the total length, and then we multiply it by 4. Why? Because it will be 4 meters away from R1. We want to make sure that we're exactly halfway. So we'll have 6, we'll have 3 meters, and we'll have 4 meters on the other side. So this will be 4 meters. Cool. Then we've got our 50. Our 50 will be exactly 10 meters away. So if and the anti-clockwise will be R2 times 7. If we total that and divide everything by 7, we get a final answer of 442.857 kilonewtons. Then we look at some of the anti-clockwise moments about R2. Where is our point of focus? We are focusing on R2. Anti-clockwise moment will be our 80 by 5, which will be moving in that direction. And then we also have our 50 by 12, which is also moving in that direction. Those are our anti-clockwise. And then for our clockwise moments, we've got 50, which is a concentrated load moving in that direction, and we've got R1 moving in that direction. So add everything up, we get 607,143 kilonewtons. We balance our upward and our downward forces, and everything should add up to 1050 kilonewtons. Our next step is to calculate the bending moments. So we've got our principal points, which are R1, point number B, and R2. So what we are looking at, the downward forces, we look at them as negative, and the upward forces are seen as positive. Now what we have here, we have 80 multiplied by 2, and negative 50 times 2, which gives us a negative 260. Then bending moments at B our AT is now at 5 meters, and we take half of that 5 meters, which is 2.5. Our 50, the weight of our beam, is also at 5 meters, and we take half of that, which is also 2.5. Then our R1, which is 607.143, is 3 meters away from the left, and we multiply it by 3, it gives us 196.429 kilonewton meters. Bending moments at R2, we've got our 80, the total of our 80, which is 80 times 5, and then if we take the half, which is 2.5, and we add the 4, we'll have a distance of 6.5, and then we take away 50 times 9, which we're only focusing on the 9 meters, and half of that 9 meters is 4.5. And the R1, we add it, and if we look at the distance, it's 7 meters away from the left. Gives us negative 375 kilonewton meters. What we need to remember is that the shear force at any point along a beam is a rate of change of the bending moment. So anywhere where we're calculating the rate of change of the bending moment. So also what we are looking for is that if a bending moment is at a maximum or a minimum, where will that be on the shear force? It will be at the point where the shear force is 0. So at the 0 point, it's either we'll find the maximum or the minimum bending moment. Shear force diagram, what do we have? We've got first triangle, which is on the negative side from the 80 kilonewton per meter and the 50 kilonewton per meter. We've got our first triangle, then we've got our next right angle triangle for bending moment, and we've got this small one over here, small triangle at that point. Okay, that's another triangle on the negative side. Then we've got trapezoid. This is on the positive side, and those are our points. Now what we are also focusing on, we need to find this point over here, which will give us, let's see, it will give us the maximum bending moment. So this is where we'll find the maximum bending moment. Remember, we said wherever our shear force makes a 0, that point will either give us a minimum or a maximum bending moment. So the points that we're going to be working with, we have A on this side, we've got B, this was our C, this is D, this is E, and we will call this F, the new point, the maximum. We will call that our point F. Why do we need this point F? It's for our maximum bending moment. What are we going to need from this point? We're going to need the base of this triangle over here, and also the base of this triangle over here, because these points will be starting from our 0. Now we need to use the area of the first triangle, the area of the second triangle, to give us our maximum bending moment. The bending moment diagram. We've got our points that we need to first note. Let's use that. Our point number B. I need something thinner. point number B and point number F. Point number A will be the start of the bending moment. This would have been C. This is D. And at the end, we've got E. E. But the main points that we were interested in are B, F, and D. Sorry. So on the previous slide, we looked at this distance here. And we said we're going to use yellow, right? And for green, it would be B to F. So we were looking for that. Now we wanted to find the base of the triangle. So from A to B, what do we have in yellow? We've got the distance from A to B, or the base of triangle AB, is 2 meters. How do we get the 2 meters? We use the load over the UDL, which is 260 over 80 plus 50 gives us 2 meters. And then for triangle B to F, what do we use? Load over UDL. What is the load? 347 over 130 gives us 2.67. How does that help? Anyway, helps us to find the maximum bending moment. So it's going to be this calculation at the bottom. We've got this positive side of 347, the positive triangle, minus the negative triangle of 260 times 2 times half. And it gives us the maximum bending moment. Put the maximum bending moment in lipstick red. That is our maximum bending moment at that point, and it's 203.436. Great. What are we looking for here? We are looking at the maximum bending moment. We want to see the sequence. The maximum bending moment corresponds with the 0 point on the shear force, and it goes all up to our 20 kilonewton point load, and that is right in the center of the beam. Here's a correspondence of the 10 kilonewton to the 0 line and to the maximum bending moment. Now we see a correspondence of the 3 kilonewton to the 0 line to the maximum bending moment. And in this example, we look at the correspondence of the UDLs, the 0 point, and the maximum bending moment. Thank you very much. Please look at other examples in your textbooks and join us next time as we look at the cantilever. Thank you. Bye.